All right, so we've got the equation of the function of f of x equals 2x minus 3. And so we got a few points on here I want to be really explicit about. You've got 2, 1. We also have 0, negative 3. And a couple others. Let's see, we got 1, negative 1, 3, 3, 4, 5. And what's this? Negative 1, negative 5. And you've got all the rest of the points in there as well, but going to use these points here kind of as some tools to help us um, as we change them, reflecting them, and kind of checking out what happens. So here we go. So y equals negative f of x. And if you were to look back up to your notes at the top of the page, you'd see that, hey, when I had y equals negative f of x, that was a reflection in the x-axis. So let's kind of just play with this here for a moment, though. If we had plugged in 2 into the function, so before we were getting 1, now if I plug in, and remember this is negative f of x, so we're going to find f of x and then multiply it by a negative 1. If I plug in 2 for x, 2 times 2 is 4. And again, this is going to be y is equal to negative f of x. So 2 times 2 minus 3. So I've got 4 minus 3 is 1. But now I'm going to make it negative, where before I was getting positive 1. Because of the negative up front, it's now negative 1. Where I'm plugging in 3. 2 times 3 is 6. 6 minus 3 is 3. And before I was getting positive 3, but now I'm multiplying by this negative, and I end up with negative 3. And we're going to continue on. You can plug in the rest of these, plug in the rest of these points. And what we're finding is that this is, in fact, reflected over the x-axis. All right. It turns into the line of y equals negative 2x plus 3. A negative 1 really has been multiplied by that whole function. That once we know what the function is, we distribute in that negative 1, and here's our new equation. And again, just this is a x-axis reflection, where we have x comma negative y. All right, the second one. This time not necessarily a reflection or not a full reflection, but we're getting the results of f of x using that same function, but at the end of it, going through the absolute value function. So kind of looking back over at our parent graph here, all of these values, all these output that are positive y, they're all still going to be positive, and nothing's changing there. So got 2, 1, 3, 3, 4, 5, because if I plug in 2, I go through, I get 1. The absolute value of 1 is 1. So nothing's changing here. In fact, nothing's changing all the way until it hits the hits the x-axis. Right there at 0, everything's still good, still groovy. However, once we plug in numbers like 1.4 or just even 1, if I plug in 1 into x, so we're taking the absolute value of 2x minus 3. If I plug in 1 for x, that's 1 times 2, that's 2. And 2 minus 3, that's negative 1. But the absolute value of negative 1 is 1. And if I plug in 0 and I get, that should have been a negative 3 from earlier. If I plug in 0 and get a negative 3, I'm going to take the absolute value of that and get positive 3. And here's our graph. Okay, absolute value of f of x. So yeah, there we go. Absolute value on the outside. So you're completing the function of f of x. There's no negative number being input in for x. Or sorry, when we plug in just an x, we get the same x values. It's really afterwards, just once we've got the result, once we've got our output, then we are making those values positive. So we never have a negative result. If we had had a negative on the outside, this isn't the case, but if we had had a negative on the outside, we'd have the negative version of that graph. If we'd had that negative on the outside, which we didn't right here, but we could have that a little bit later on. Next, we have y equals f of negative x. So this time we're making the input negative before we even put it in. So let's rewrite the function here. 2x minus 3. But now when we plug in x, we're going to make it negative before even plugging it in. So if we plug in 0, nothing should change because 0 times negative 1 gives us 0 still, and 0 times 2, minus 3. So we still have the point 0, negative 3. But now let's plug in 1. If I plug in 1, then first I need to make it negative. So 1 becomes negative 1. Negative 1 times 2 is negative 2. Negative 2 minus 3 is negative 5. If I plugged in negative 1, however, negative 1 is positive 1. And so positive 1 times 2 is 2, and 2 minus 3 is negative 1. All right, so again, what's happening here is we're taking all the x values, and before we even really plug them in, we make them negative, make them opposite, and then plug that value in. So we end up with a graph looking like this. All right, and it is a y-axis reflection, where the original parent graph was heading up right here. This one's been reflected across the y-axis. All the x values have been swapped. All right, and last we have x equals f of y. And so what we're going to be doing here is reflecting it over the y equals x line. So here's y equals x, roughly, and our original parent function here is right there. And everything's getting mirrored over this line. So when in half a point, it's coming out over here. This was the point of, let me go ahead and do it in blue. This was 2, 1. Now we're getting out 1, 2. X and Y has been switched. Where we had 0, 3, now we're going to have, or 0, negative 3. Now we have negative 3, 0. And we're going to be graphing this line right here. All right, so again, swapping our x and y values, where we did have x comma y, now we have y comma x. Okay, and so our new graph, we've got y equals, our slope's going to be 1/2 and plus 1/2 x plus that's going to be at 2/3, 1.5, or sorry, 3/2, or 1.5, and there we go. So this one is going to be the inverse. We'll kind of get more into that a little bit later on, but this is the function that undoes the original function of 2x minus 3. So we'll get more into that a little bit later on, though. All right, hope that helped.